So, good morning all together. I welcome you to today's webinar, Machine Automation Customizations, 3 Use Cases. My name is Meinrad Happacher. I'm Senior Advisory Editor at Computer and Automation, and I'm honored to host the webinar over the next 1 hour. And you all know, I think, we are currently experiencing a very strong trend towards a customer-specific adaptation of products, and thus also of some manufacturing machines and factories. And our speaker today, so I hope I pronounce it very rightly, Yves Delabroise, will taking in an in-depth look at this topic in the next hour. He will present 3 use cases that show how controllers and machines can be adapted to these customer-specific requirements. Hello, Yves. Thank you to stay with us. Thank you very much. And you know, Yves has more, maybe you know not, Yves has more than a decade of experience and expertise in automation engineering and real-time systems. His knowledge covers many areas from industrial communication standards such as EtherCAT and OPC UA to motion standards and such as PLC Open Motion Control. And now he will refer in his presentation to the Kingstar product line. That's a software platform for machine automation for Industry 4.0, which he was instrumental in initiating and developing. So I think, Yves, the stage is yours. Maybe just one last remark to the participants. At the end of the presentation, we will have time for questions and answers. Please write down your questions in the control board on the left side under questions or Fragen, you know. And now, Yves, I think the stage is yours.
Okay, so hello everyone. So I'm Yves Delabroise, architect for Kingstar at Interval 0. So the presentation today, as mentioned before, will be presenting the customization of machines. So we will first present why customization, why it is asked for so much. Then the different customization types from a technical point of view. Then we will present the Interval 0 company and the Kingstar product line. And finally, we will present the 3 use cases where we show how customization is needed and how it is implemented. So first, why make a whole webinar on customizations? Well, customer products now have yearly updates. They even have special editions. The trend is going to what is called batches of one, where the customer, when purchasing, can select a customization, different colors, different shapes on their products when they are ordering. So the machines must be able to produce many different types of hardwares and customize each of them in some cases. Machines are still used for decades. Therefore, they have to support multiple products. And with new products, they may require some new functions, some new hardware that was not ready yet when the machine was originally built. So machines need to be able to be modified when they are deployed and even after they are deployed. So this creates like a chain of customization. The controller developers, they want to add their own market-specific features to the machines, to the controllers, because that's what differentiates their machines from their competition. Then the system integrator or the machine builder, they will want to select modules for each project. They can have different grades, different precision levels, different tests such as inspection, such as sorting, that may be added or removed from a machine. Then the manufacturer who is buying the machine, they want to integrate this machine into a production cell, a production line, and the factory. This means communication with other machines, with supervision systems, and even now with the cloud. And at the end, the operators need to be able to execute different tasks on the machines, because when you customize a product, you want to select the color, you want to be able to build multiple. If it is, for example, an engraving machine, it must engrave different shapes, different pictures on different hardware. Therefore, they will want to be able to have a task system, a task format that they can select from. So the most important things now when developing machines is the customization. This customization will be needed for your machine to be able to be used in many different ways. Kingstar is an automation platform that has been developed to be used with customization, to be open for modifications at every level. So the next step is, what are the different customization types that you have on a machine? So the first one is obviously the hardware. When you build a machine, for example, a robot, you will want to have different payloads for your robots. This means that you will have different models of hardware, different motors for the different hardware. You may also have a different precision level for your machines when the company builds a range of machines. Therefore, you will use hardware from different companies for each precision levels. It is necessary to allow the customers to mix and match the payloads, the different types of payloads, the different types of precision when they build the machines. And the machine will be used itself for more than a decade at least, usually 2-3 decades. This means that the hardware will evolve during this production. Therefore, the machine, the controller of the machine, must support multiple types. Otherwise, if you have one controller, if you build and design one controller for each machine type, you will have many sorts of control in your company, and the maintenance will be very expensive and very painful. The second customization type is adding modules to a machine. As said before, this is, for example, like test benches or production lines. You will have different options in the machines. The customer will select, depending on what product they want to produce, which options they need and which ones they do not. Therefore, the modules will be added to the controller. The controller itself is expected to support all the different optional modules. But nowadays, with the new technologies, it is possible to do even better. Controllers can detect which modules are connected without the need for any customization or updates. It will detect, identify the modules, and adapt itself by loading the corresponding software for all the attached modules. It is now even possible with protocols such as EtherCAT to add modules to a running machine. This means that the controller and software can be added and applied to a new module that is running while other modules are still processing. The next step is what we call kernel tailoring. The kernel part is really the controller, the platform for the controller, the one that will be reused in all the different grades of machines, in all the different types of machines of the company. This kernel will require, in most cases, some market-specific functions to be added by the company itself. These custom functions are what differentiates the company. It's what the company promotes. For example, it could be a hand teaching for a robot arm. It could be a special molding system and control for plastic or other materials. These functions often need real time to run. So the customization must be, the platform that is used for the controller must be customizable in real time too, on the real time side too. Then on the non-real time or at the application level, there will also be customization needs. Some features such as an inspection module or a calibration module will use their own standalone software or their own standalone library, which may be real-time, non-real-time, on a dedicated board. The application must be able to adapt and use these softwares when they are added, when those modules are added. This is done with either open protocols or open files, configuration files that are passed to the controller so that the controller can know which modules to load, where the modules are located, what parameters to apply based on the customization. So this application needs to allow a smooth communication between the different modules and between the different features. In the next step, it's when you integrate the machine into a factory or inside a production cell. At this stage, it is necessary for the machine to communicate with other hardware, other machines, supervision system, and also an MES for the scheduling. There are two types of communications in this kind. There will be the real-time communication, which is required when you need safety or control. This is done when two machines may collide and because they will access the same space, for example, two robots loading and unloading. Therefore, we must make sure they communicate to avoid any collisions between the two machines. This requires real-time communication. If you do not need real-time communication, you will use other protocols such as OPC UA. Those can be used to communicate with other machines to produce data such as which task is running, what is the step, does the next machine is ready for unload or ready for loading, or to request a new task. This later on, there are standard protocols now being developed with OPC UA, TSN, EtherCAT that allow smooth integration. But there are many older machines already in the factory. Nobody will replace the whole machines at the same time. And there are possibly, or most likely, already automation protocols used in the machine for communication with SCADA and with other machines. For this reason, the machine builder must allow to add extra protocols on the machines or add extra IOs for this kind of communication. The last step is the task customization. The most well-known or popular task customization is the G-code and CAD drawings used in CNC controllers. So for many other types of application, there is also requirements to provide a way to decide which task, which precision, which cuts will be done on the piece to process. And now more and more, there is this concept of batches of one. Batches of one is when every piece has a different task to be processed. At this point, it is not possible for the operator to load a new task and select a new task for every piece. In this case, you need a communication with a task database, and the machine will read an ID or a barcode on the piece and automatically select the right task from this database and use it to process the next piece. So the next step, I will present shortly our company Interval Zero and the Kingstar automation platform. Historically, Interval Zero has been a company focused on Windows-based machine controllers. For over 20 years, Interval Zero developed and maintained the RTX product line, providing a real-time extension for Windows. RTX is used with control and communication boards to build machine controllers. As the power of processors increased and new Ethernet-based field bus emerged, customers asked us repeatedly for software protocols and software-based control logic. Therefore, Interval Zero developed the Kingstar automation software platform to build machine controllers with these new PLCs, software PLCs, and protocols such as EtherCAT. Kingstar is based on 5 different products. We have the Field Bus, which is based on real-time operating system and the EtherCAT master, the motion control, the PLC, software PLC, vision, and IoT. Kingstar runs on the 64-bit version of the real-time extension RTX of Interval Zero. It allows applications to be developed in real time with C++ in Visual Studio and on the Windows side with any development environment. It can be used on a wide range of computers from 2 to 64 cores, and it is deployed in many different industries such as robotics and automation, but also medical, defense, and simulators. The Kingstar Fieldbus implements a plug-and-play EtherCAT stack based on automatic configuration. What this means is that we use the EtherCAT bus scan features to detect what hardware is connected. And then instead of using a configuration file, we have a database of hardware. We match the connected hardware with this database and features requested by the application to automatically build a configuration. This means that the software on top of the Kingstar Fieldbus will be able to adapt automatically to connected hardware. We will provide it with the list of hardware available, and it can use EtherCAT hardware as if it was local variables, local devices, without having to understand how EtherCAT works. On top of the Fieldbus, we have the motion based on the PLC Open standard motion control libraries, and most likely the CAN drive profile to communicate with the drives. We provide the motion control for standard point-to-point, synchronized motion like electronic gearing, camming, group motion with linear, circular, helical moves, and we have the flexibility. Each axis can be simulated, virtual, a real axis. It can have its own control mode, and it can be a master or a slave and a slave at the same time for different moves. The communication with the drives is done through the CAN drive profile that can run on EtherCAT, and the interpolation is done on the master side. But the PID and the tuning can be done either on the master or on the drive, depending on the requirements. With the new powers of CPUs, we are able to run a large number of axes at fast cycles. For example, we have a customer running 20 axes at 125 microsecond cycles, or other customers using up to like 60, 64 axes with a 500 microsecond cycle time. And each axis, each I/O can have its own different hardware brand and control mode. The next component that we have is the Kingstar Plc. It's a standard, fully featured IC6131 PLC. The specialty of this PLC is that it is very flexible. It can be customized by us and by the controller vendor, the controller builders. It can be customized on the real-time side to add new protocols, new features, but also on the Windows side, on the UI side, to fully white box it or add special features and special UI to control those features. It also includes an OPC UA server for the communication with other machines. The next piece is the Kingstar Vision. The Kingstar Vision is a real-time GigE stack that can be used like a software frame grabber, removing the need to have a PCI board for a real-time and stable frame grabbing. But it can also be used with, for example, with OpenCV to run the vision in real time. And whether the vision is real time or not, you can still timestamp all the images when they come in the real-time system to have a synchronization between the vision and the motion. The last component is the IoT piece. Kingstar is based on Windows and RTX. So you can use any cloud, any protocol, any updates and security features that are available in these environments. We have frameworks and third-party software that can be used for data sharing and local processing for analytics. So this is the Kingstar architecture. It is based on a computer, a normal x86 computer, and you will have two spaces, a real-time space in RTX and a Windows space. Mostly the kernel will be on the real-time space because it will run the processing in real time. In this area, you will find field buses such as GigE and EtherCAT connected to some hardware. Then on top of it, you will have the motion and possibly any application that requires real-time control from the user. And at the same time, you have the Kingstar PLC for users who want to develop applications with a PLC that runs in real time. On the Windows side, you can use any IDE that you prefer to develop any sort of applications. We also have an IDE for the PLC development, and you can connect to the machine with OPC UA or Modbus natively, but you can also add your own protocols or boards. There is no restrictions on what is running on the computer, neither on the real-time side nor on the Windows side. And of course, you can use Azure and other Windows system for software updates and cloud management. We are now coming to the most important part of this webinar, which is showing exactly in real cases how this customization is needed, where it is needed, and how we fulfill these needs with Kingstar in some of our customers. The first use case that we provide is PCB, printed circuit board processing machine. This machine will take a PCB board into a treatment chamber, and then it will take it out, possibly flip it if it wants to process both sides, and possibly inspect the results or sort the results. This machine has to be designed as modular because the treatments, there is a wide range of possible treatments, such as exposure units. And then you will have different types of boards where you can have 1 layer, 2 layers, where you may need to flip the boards. And you will have some different types of inspection and testing to be performed at the end. Our customers selected Kingstar for this machine because the platform provides them the flexibility and easy integration. They use Kingstar Field Bus because it has plug and play for EtherCAT. Therefore, they can automatically detect which modules is connected, and their software will adapt automatically. The end user or the integrator will not need to change configurations when a new module is added or when they assemble the machine. Everything is done automatically by the controller by detecting the hardware that is connected. You can also make the machine evolve after it is bought by adding modules to this machine. Adding a module to the machine is as simple as just connecting the power and the RJ45 cable to the modules from the main machine to the module. In terms of architecture, they have different tasks. So the loading, the flipping, the unloading, and the positioning of the boards is done using standard motion provided by the Kingstar motion system. But then everything which is inside the PCB processing system is the IP of the customer. This is what their company is known for, and this is their specialty. They can add this in real time to control any types of hardware they have, even hardware that they designed themselves. And provide the team that builds these features can provide it on the side of the Kingstar Motion for the team that build the application. The application itself can have a state machine in real time to control how the machine moves, and then a UI in Windows. When the module that does the visual inspection is plugged into the machine, they will have a third-party vision software running on Windows and connecting to its own hardware. The second use case that we want to present is a test bed. We have many customers using test beds in automotive, avionics, and other industries. Of course, a test bed is very modular because you have one module for one test. So similarly to the previous machine, the PCB machine that we presented, you will have a modular machine with many options, and the controller should adapt to these machines. But one thing that is special for these test beds is that often as they are doing tests for specifications which are official, these specifications evolve. Therefore, they need to build new tests, often with new hardware, and add it to a machine that is already deployed. And as the test may run for multiple days, they do not want to restart the machine when they add a module. So they must be able to add modules to a running machines. This was possible for them using Kingstar. They used a feature from EtherCAT called Hot Connect, and another feature which is in combination with the automatic configuration from Kingstar. Normally, the Hot Connect feature is a feature from EtherCAT that allows you to add some hardware, a hardware group, on a running network without needing to stop the other hardware. So the machine and the control still runs properly. You add a new module, it will be detected, and your software can now start using it. But in their case, this is not enough, because in the normal Hot Connect, you have to provide the software and the possible connected hardware when you start the machine. And in their case, the hardware may be designed afterwards. But with automatic configuration and plug and play from Kingstar, we do not require this configuration to be provided for EtherCAT. When a module is connected, we will run the automatic configuration on that module. And because you can have multiple applications running on one EtherCAT network, they can load a new file or new module or new application that will control this newly added hardware without modifying the rest. But to do this properly, they need to have their own architecture to communicate between the different modules, communicate between the different tests, so that their main application, their main UI for the customer can detect that a new hardware is added, can load the new software that may have been copied through the network or with a USB, start it, and add the new test in their processing schedule. The last use case that we present is a robot arm. A robot arm is typically the best use case for customization because it requires all sorts of, almost all the types of customization. A robot arm comes in different payloads and in different shapes and precisions because they range from applications from pick and place to welding, and they have payloads from a few grams to tens of kilos. A vendor will not have only one model of robots. Therefore, they will have models with 4-axis, 6-axis, 7-axis, with wide range of payloads and possibly multiple ranges of precisions. They need to have one controller for all of these. Otherwise, the number of combination is just too great for them to maintain, and it's just too expensive to have enough engineers to develop and maintain each of the controllers. But not only that, robot controllers will have special features such as force control and hand teaching. Hand teaching is so that you can just teach the position for a pick and place robot by moving the robot instead of having to code the exact position, which is much more difficult as you have to do a lot of try and error. But they will also have force control for, like, for example, scratching. When you have a pick and place robot, it may pick a brand new process piece and put it in a box. If it scratches the piece because it's touching something while it moves this piece, then the piece is broken and useless. Therefore, the robot must be able to detect that there is some resistance when moving the piece and choose a different path to avoid any scratching or any breaking of the piece. And last thing, robots very, very rarely work alone. They will need to collaborate with other robots, with machines such as CNCs, or with production lines. Therefore, they will need to have some standard interaction methods with those other systems. So those different integration methods, I will not go again on the plug and play feature that allows that is the reason why many customers choose Kingstar for their robots, as I presented it on the previous use cases. This time, I will present those specific collaboration methods between robots and other machines. The first mode is what's known as master control mode. The robot controller is the master of the whole system. Usually, you want to avoid having multiple applications and multiple controllers in one production unit, because that means you need to synchronize between more costs and more synchronization effort between the different applications. So when you connect a robot to a conveyor belt and other IOs, most likely you will want the robot itself to control the conveyor and control those other IOs. This is what is known as the master control mode. The controller inside the robots will be controlling other drives and other IOs. They can be added easily when you use EtherCAT because you just have to provide an out port on the robot controller, and this can be used to daisy chain new hardware to the controller. Then it needs to be programmed in the application by the end user and not by the robot controller. This is done easily with the Kingstar architecture in the PLC or in the UI because the controller will detect the new hardware and make it available to the user application. The second mode that is often used is a peer-to-peer mode. Peer-to-peer mode is when you have multiple machines which are mostly independent and need to talk to each other to process things in order, such as loading, processing, unloading, inspecting a piece, or to avoid collisions. If multiple machines can reach the same place on the system, you need to make sure that they do not reach it at the same time. So this is done, it will be done in the future with new protocols such as OPC UA. But at the moment, most machines do not support these new protocols, so it is done with either a networking protocol or with most simply I/O connections. This again means needing to add extra IOs or an extra protocol hardware on a PCI board to the system. One more thing to note is that when you do collision avoidance, you need real time, because if you are using a normal protocol, normal Ethernet to exchange this information, you do not know if it is outdated or not. Therefore, in that case, you may want to use a real-time protocol such as EtherCAT for communication between the two peer-to-peer machines. The last mode is the slave mode. This is a use case which is very typical to robots. When a robot is used, for example, in combination with a CNC to do loading and unloading, the CNC is the main controller. You do not necessarily want to write a second application in the robot just to tell it where to pick a place, when and where to pick a piece. The easiest method is to write only one application in the controller of the CNC. To do this, both controllers need to have the same way to communicate. This is often possible because both CNC and the robots implement a standard PLC. So instead of writing the application in the PLC of the robot, you write that application in the PLC of the CNC, and that CNC will transmit the command to the robot controller over a real-time protocol. So the interpolation and robotics control is still done by the robot controller. The robot can be taken and used on a different production line with a different mode later on. But there is no application, no program written in the robot for this CNC and robotic application. There is only one program, and it is written fully inside the CNC. This makes the development much simpler because the synchronization is automatically done inside this application. So this can be done easily with Kingstar for the robot arms because they can add their own custom IP like the others did, but they can expose this custom IP to the PLC. This can add new features in the PLC. Therefore, their end user can develop either with a scripting language through the GUI that they provide if they are using basic the robot standalone or the robot in the master. But when they want to do the synchronization of the new IOs or program for the new IOs, they can do it inside the PLC. Usually, the vendor will not want the customer to develop their own real-time application. This could be dangerous and conflicting. So they can force them to do it in the PLC with standard motion, standard IOs, plus their robotic special functions, and they can hide some hardware from the PLC so that the user application cannot send commands to hardware they don't want them to, such as hardware inside the robots. Then third parties such as Vision for the detection and other software can be all added on the Windows side. You can also add PCI boards there are existing some PCI board that can support any protocol for the communication with peer-to-peer other machine and with the cloud. Also, we already provide the OPC UA interface to communicate with the cloud and the IoT applications. Thank you for listening to this webinar. So once again, the conclusion is that the customization is really a very important and critical requirement now on machines, because one controller, one machine will have to be useful for multiple projects, multiple pieces. It can be modified after it is deployed. People may want to add new hardware to it. There are also other important topics such as security, remote assistance that we may talk of in other webinars, but these imply updates of the software, updates of the controller. And this is also very easy on a Windows platform with RTX, which is open and where you can download new programs and new updates just as you would update your Windows computer. The next important piece is the communication between the different functions, the different modules inside the machine, and between the machine and other machines, other hardware. They are now standard and open protocol to do this. The ones we believe are the best suited are EtherCAT and OPC UA, because they are very standard, they are open to many different vendors, many different hardware vendors, machine vendors use them. So you will be able to find the products you need, the interfaces you need in these protocols. The next thing is that you always have to think about the future, about how things will evolve later, about new features and new needs that we do not yet know about. And the Windows with RTX platform is very flexible for this. It is based on an x86 PC, any computer, usually industrial because you want to be able to buy it for a long time and manage it properly. But you can even run it on any computer that can install Windows. With this solution and Kingstar, which already implements open protocols such as EtherCAT, OPC UA, and Modbus, you will have an easy pass to the new features, to the Industry 4.0, communication to the cloud, and newer protocols that come in. Thank you for listening. We will now move to the question session if you have any questions about this. If you want more information, you can also contact us or go evaluate the Kingstar platform on our website.
Okay, Yves, thank you very much for the great overview. As Yves told, please write down your questions if there are some. Maybe I will ask a first question, Yves. As I understand it, Kingstar only supports EtherCAT up to now. Do you plan to support other protocols like Profinet or maybe in future TSN, for example?
So yes, we rely on EtherCAT because it is very open and future-proof. So for other protocols such as Profinet or Modbus or even CanOpen, there are some couplers in EtherCAT that allow you to have a mixed network, such as EtherCAT plus CanOpen, EtherCAT plus Profibus.
Okay.
Ourselves, at the moment, we do not plan to have a full Profinet stack because Profinet is more closed. There is less demand for a custom platform. People using Profinet usually buy everything from Siemens. On the side of TSN, this is a protocol that it's not a protocol. It is a tool to enable other protocols like OPC UA, and we are following this. It is not yet ready for use inside a machine. It can be used on the Windows side for communication between machines. This is already available. We have OPC UA, and TSN can be added on the Windows side. There are features for that. Once it comes down, maybe on the field bus, we will follow and we will support it. Yes.
Okay, good. So maybe another question about the performance. How many drives do you support and at which cycle time?
So in terms of performance, it will depend on the CPU, mostly on the cache of the CPU. Things run most smoothly when the whole kernel logic can fit in the cache of the CPU. So like the numbers that we gave from some of our customers, they can have easily up to 20 axes at very fast cycle times, such as 100 microseconds, 125 microseconds. If you are in cycle times that are slower relatively to EtherCAT, like 500 microseconds or 1 milliseconds, you can go to larger amounts such as 50 axis, 64 axis without problems. If you go above, there will be no problem with EtherCAT. EtherCAT can support multiple thousands of IOs and drives on the same hardware. Even in terms of logic, they can still run on the computer. What will most likely cause delays, it will be the cache. If the application is too big and can no longer fit on the CPU cache of the CPU, we will need to have back and forth of data in the real-time cycle with the RAM, which is slower, but it can still work. So it will be, depending on the hardware, you will have to have a faster CPU. But like an i5 can run 20 axis at a very fast cycle time, or 50 axis at a normal cycle time on EtherCAT.
Okay, great. Okay, and maybe one more questions about slave getting into your applications. If I'm using special slaves that you don't have tested up to now, is it compatible with automatic configuration, or how can I get them into it?
So yes, so we provide a database which is always evolving, where we test the hardware, we know what is working, what is not working, what features are compatible, and those work automatically. It is always possible to override these settings or to add new settings. We provide a tool with a runtime to import an ESI file, which is the standard file format for slaves, and to add it to the database. So this way the customer can have the database that we provide plus their own database that has higher priority than ours. So when they start, they can add hardware or they can override settings for the hardware that we provide.
Oh, great. Okay. And what's about the mechanics? If I'm using a mechanics of my machine which is particular, is it possible to use my own kinematics and pit with standard motions, or what? How is it going on?
So yes. So and the way I presented, in most cases, the customers, like with robots, they have their own motion, their own kinematics, their own PID, and their own setup on top of the Kingstar field bus. But we have some customers, they want to use our own motion with special PIDs or special kinematics. In that case, what happens is that we can have virtual axes. And so the standard motion is running on a virtual axis, and then the customer application, because they can have their custom IP in real time, will take the output of this virtual axis, process it with their own kinematics, their own PID, and then inject that into real axis and real hardware to control them. So this way they can add a layer in between a virtual axis that uses standard motion and a real hardware that has a different kind of architecture.
Okay, great. Thank you very much, Yves. So if there are no more questions, let's wait just a moment, but I don't see one more. Then, Yves, I would say thank you very much. It was a very interesting topic. And if anyone has any questions, we see the link down at your brochure, at your slide. And feel free to contact Yves, and to all participants, thank you very much for listening, and have a nice day, and I hope we see us again very, very soon. Okay, thank you very much, Yves.
Thank you, everyone. Thank you for your help.
Thank you. Bye-bye.
Bye.